In our next section, we're going to look at the FabricPath feature set on Nexus 7K and 5K, which we'll see is going to be used to do MAC and MAC routing, or basically layer 2 routing, as a replacement for spanning tree protocol. So first up, we'll talk about just in general, what is FabricPath behind the scenes and how does the overall design work? And then we'll look at some configuration examples for it. We'll see this feature is very, very simple to configure. There's not much customization. There's not much syntax that's involved with configuring the feature. It's kind of meant to be one of those plug and play things where you just turn it on and everything automatically is provisioned and happens for you behind the scenes. Now, with our current design, when we were talking about regular layer 2 spanning tree in the switch fabric between the trunk links of the switches, we saw that when we were not doing port channels and we were configuring just regular trunks on all of the interfaces between the switches, depending on where we had the root bridge elected for spanning tree, this determined what ports would be elected are root ports and which ports would be alternate ports that are blocking, or in other words, that we're not able to use in order to learn MAC addresses and ultimately forward traffic. So with the default behavior of our network when we're not doing port channeling or not doing VPC, was that we had active standby forwarding, or what again is sometimes called the bandwidth bisection problem. That we have 20 gigs of connectivity to the upstream switch, but we're only allowed to use 10 of that because spanning tree is blocking the alternate link. Now, one of the potential solutions that we saw for this was to channel the ports together. So if we configure a 20 gig port channel between the switches, then the port channel would become the spanning tree root port, and we would not have any blocking. However, if we have these cross connects between multiple switches, even if we are channeling these together, we would still see that one of the channels would be elected as the root port, one of the other channels would be the alternate blocking port, and likewise we would not be able to send traffic in both directions in order to get to our final destinations. So even though we're aggregating the bandwidth of multiple links between the same switches, when we go to additional switches, we're going to still have that bandwidth bisection problem. Where here in this case, we have 40 gig of bandwidth in the fabric, but we're only allowed to use 20 when we're doing normal regular port channels. So the second solution for this then is the virtual port channel feature, the VPC, where VPC is taking an environment where we have a physical triangle like this, and we're turning it into a logical point-to-point link. So from 5K7, we would have links that go up to 7K7 and 7K8. But from the downstream switches point of view, we see this as a logical point-to-point connection. So instead of having 20 gig of bandwidth that's active, 20 gig of bandwidth that's standby, we would have a 40 gig channel that we can do active-active forwarding between. Now, the potential limitation of this feature, though, is that the physical topology is only supported in exactly one design, where we have two upstream switches that are channeling to a single downstream switch. So this means that if we want to add a third switch into the upstream fabric, we're still going to have that potential problem with doing blocking for spanning tree, because spanning tree still does run over the virtual port channel behind the scenes. So what I mean by this is that if we were to take another switch in the core, and let's say that we have 7K9, if we have a VPC that is going this direction to these switches, so with the channel is formed there, and then we have another link that goes to 7K9, we're still going to have to make the decision between these two, which is going to be the root port and which is going to be the blocking port. So even though we're kind of fooling spanning tree into doing active-active forwarding with virtual port channel, we still have the process that runs behind the scenes, and if there is a failure of the VPC or a failure of any of the links, spanning tree is going to have to react to that. So FabricPath then is basically an alternative to designs like this, where we want to have any-to-any forwarding without having to follow this strict exact VPC type design. Now specifically, the way that it does this is instead of using spanning tree for forwarding, we're going to use regular layer 3 routing logic, and specifically we use IS to IS routing, or the intermediate to intermediate system protocol behind the scenes in order to make what is normally a layer 3 decision. So in this type of case, what a FabricPath network would normally look like is what is known as the spine switches and the leaf switches. So the leaf switches, you could basically think of this as the access layer, and the spine switches is going to be the distribution layer or the aggregation layer. Now, in the case of FabricPath, what we're going to do is, by configuring these links no longer to run Ethernet, but instead to be encapsulated inside of FabricPath, we're going to form a routing adjacency with IS to IS between all of these switches. Now, IS-IS, without having to get into all the details behind the scenes, IS-IS is a link state protocol very similar to OSPF that routes based on the shortest path between two nodes in the link state graph. So the idea here is that if we're trying to move traffic from server 7 to server 8, and we look at this from normal Ethernet forwarding rules, what would normally happen is that when server 7 wants to get to server 8, it's going to send an ARP. Okay, we're assuming we're talking about IP version 4 forwarding. So we send this ARP request, and we're trying to figure out what's the mapping between the IP address of server 8 and the MAC address of server 8. So we send this ARP request, it goes out our physical link, it gets to the upstream switch. The upstream switch is going to send this everywhere. It's basically forwarding the broadcast out every port except the port that it was received on. Now this switch, 5K7, knows what the source MAC address of server 7 is. It knows that server 7 is located on this port E11. These packets flood up to 7K7, they flood up to 7K8. Likewise, these two switches now know where the source MAC address of server 7 is located. So they continue to do the flooding basically out all of their ports until eventually the ARP request gets down to the final server. At this point, we then send the ARP reply. The ARP reply is going to be a unicast back to this MAC address. And when we forward traffic in the reverse direction, now the switches in the middle are going to know about the source MAC address of server 8. So in other words, the switching table, or what we could think of as basically the layer 2 routing table, is built on the switches based on packets in the data plane, causing a change in the control plane. Now, this is fundamentally different from layer 3 IP routing, because IP routing is control plane oriented, in which case we have to advertise between the routers what the destination segments that we're trying to reach. Where typically in an internal network or like a LAN environment, we would be advertising this with OSPF or EHRP or maybe even IS to IS. And then between autonomous systems like to the internet, we would normally use the BGP protocol to use that, the Border Gateway Protocol. But the point being is that if I want to reach some remote destination, like I open my web browser and go to google.com, I'm not flooding my packets throughout the internet in order for the internet to figure out where is Google located. They're already going to know that in advance by having the control plane actively built, by having the routing protocols advertise where the IP space exists in the network. So FabricPath uses that type of layer 3 logic that says, well, instead of building the network based on flooding the packets everywhere, why don't we advertise which switch is connected to which end host, and then we'll build the topology based on using regular layer 3 routing logic. So specifically what happens behind the scenes is that each of these switches is going to be assigned a FabricPath switch ID. Now, if you're familiar with either OSPF routing or IS-IS routing, how link state routing works in general, what this switch identifier essentially is the router ID of the node in the link state graph. Like in the case of OSPF, that would be normally your loopback interface that is represented as the router ID in the link state advertisements. Now, ultimately, what the goal of the link state protocol is to find the shortest path between all of the nodes in the graph, but not necessarily the IP routes or the actual routing information that we're advertising based on the upper layers. So if this was an OSPF network, what OSPF's job would be to do is to find the shortest path between these 4 switches. So if we're on 5K7, I would say my shortest path to 7K7 is in that direction. My shortest path to 7K8 is in that direction. My shortest path to 5K8 could be in multiple directions. Because as long as I have equal cost routes in order to get to the destination, I can send traffic this way, or I could send traffic that way. But I'm going to be able to solve this in advance before traffic comes in based on doing that active exchange of the control plane messages. And this is essentially what FabricPath is doing behind the scenes, but it's trying to solve the shortest path between the switches in the ISIS topology. Now, ultimately, once we actually go to send traffic, what's going to happen is that when a packet comes in from the server, and we have the same type of frame, we have the ARP request come in, because we don't know what the MAC address is of server 8. This is what we're trying to figure out. Now, in the case of FabricPath, this frame, which is the IP packet, okay, with the ARP payload, and we have the Ethernet header, we're then going to encapsulate this inside of FabricPath. So it's its own special frame format. It's basically like a tunnel. Okay, this frame goes over the fabric, and it's going to follow a tree similar to spanning tree, and eventually the packet is going to go out there. So it's flooded based on normal layer 2 flooding rules like you have in regular Ethernet. The difference is that when a packet is flooded over FabricPath, it doesn't go in all directions. It goes in a pre-calculated direction based on a route election, similar to the logic of spanning tree. But the endpoint is that the packet gets to server 8, and server 8 is now going to do an ARP reply. Okay, the ARP reply comes back in, and the packet's going to go in the reverse direction. But what happens in the middle of the network is when we are encapsulating the IP packets, or more specifically the Ethernet packets, encapsulating them inside of FabricPath, there's going to be a source switch ID and a destination switch ID field that is inside this FabricPath header. And you could think of this just like how an IP address works. That when I go to ping google.com, I create the packet with my source address, my source IP address, and their destination IP address. And that's how the packet is routed through the internet. It's going to look at the destination IP, and we're going to forward the packet based on what the routing table says. FabricPath is going to do the exact same thing, but it's going to be routing the packets based on the destination FabricPath switch ID, as opposed to routing the packet based on the destination MAC address. Now, one of the big advantages of this is that the devices in the core of the network, or specifically what we call the spine of FabricPath, it means that they do not need to learn the MAC addresses about all of the end hosts. The only thing that those switches need to know is what are the other switch IDs of the exit nodes out of the fabric, or specifically what we call the leaf switches. So when you look at this from a scalability point of view, FabricPath becomes much more scalable in the control plane than regular Ethernet switching does, because in the case of Ethernet, all switches would have to learn all MAC addresses. So let's say within the data center, we're creating VLAN 10. And in VLAN 10, we have 1 million different virtual machines. Okay, so not a realistic number, but for the sake of argument, say we have 1 million VMs. This means that on every single switch along the path of VLAN 10, they would need to know 1 million MAC addresses in order to properly do the forwarding. So whether these devices are at the access layer, in the distribution, or in the core, each of them would have to hold the entire MAC address table in order to properly do forwarding. But in the case of FabricPath, the only devices that learn the MAC addresses are the leaf switches that are actually forwarding traffic to those destinations. So it starts to make the control plane scaling much higher, but also from a data plane forwarding point of view, it allows us to do equal cost multipath routing, or what we call ECMP. So in order to scale this type of design, the only thing that we need to add is more connectivity from the leaf nodes to the spine nodes. So if we want more bandwidth, we could say that we'll have a third and a fourth spine. So these will be 7K9 and 7K10. And we add some additional connectivity to the new spines, and we connect the spines together. So we would have connectivity here, 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 basically a large mesh of connectivity. But this now means that when server 7 is trying to reach server 8, it's going to have all sorts of equal paths that it can route through in order to get to that final destination. And this is what the ultimate goal is to make sure that we can do not only active-active forwarding, but that we can do active-active-active forwarding. Where in the case of the virtual port channel, we're stuck with that triangle physical design that we're turning into a logical point-to-point link. In the case of FabricPath, now the topology becomes arbitrary. Because since we're using layer 3 routing logic, as long as we can solve the shortest path tree between the nodes in the fabric, we can use any of those outgoing links in order to reach the destinations. So it makes the network much simpler to provision, because the only thing we need to do is just simply turn the feature on, let routing behind the scenes solve the path between solve the shortest path between the nodes, and we automatically have equal cost multipath routing essentially through the fabric in order to get to our destination MAC addresses. Now, if you want more information about the specifics in terms of like the frame format and how we actually build the forwarding table, there's a really good write-up on Cisco's website. If you just search for FabricPath white paper, which is this one here, Nexus 7000 FabricPath. Where you could find this from the manual navigation path is if you're under the 7K documentation, it's under the white paper section. And I mentioned this section before. There's a lot of really good information here that you may want to read through before you look at something like the configuration guide in order to get a general background on the technology. Like in the case of OTV, there's a really good document here that is using OTV to extend layer 2 between data centers, or like in the case of virtual device contexts, high availability in terms of routing. In our case, we're looking at the FabricPath. Okay, if we look at some of the specifics here, for example, the frame format, what we're basically doing is taking an Ethernet packet. So an Ethernet frame has a destination MAC address, and it has a source MAC address. These two fields are normally what we're doing our forwarding based on. So when the frame comes in, we learn the source MAC address, and we switch towards the destination. So if the destination, we don't know about it, we flood it everywhere. We send it as an unknown frame. Ultimately, the end result is that all the switches in the core should know about all source MAC addresses, and they're able to do the forwarding. But in the case of FabricPath, we're no longer going to route based on this field, or we're no longer going to switch based on that field. Instead, we have this additional encapsulation. So this is the FabricPath header, and then there's a new FabricPath trailer that goes on the frame. And inside of this, we have the outer destination address, and we have the outer source address. Now, these specific fields are not MAC addresses, they're not IP addresses, they're basically the router IDs for the nodes in the fabric. So in our particular case, we have 2 leaf nodes and we have 2 spine nodes, so there's going to be 4 total switch IDs that we're going to be routing the traffic between. Now, ultimately, when the traffic enters the fabric and we go to actually forward to a particular destination, so let's look at an example of the basic tree format. These nodes here would be considered the leafs, and these ones here, these are considered the spine. Now, there's no configuration difference between the leaf and the spine. The only difference is that if you have a regular Ethernet port, you are considered to be a leaf. So you're doing the Ethernet to FabricPath encapsulation, that's the edge of the network, that's the leaf. The FabricPath spine only does FabricPath to FabricPath switching. So it has only FabricPath ports, it doesn't have any regular Ethernet ports. Now, specifically what's going to happen is that when the frame enters this way, we take the Ethernet header and we're going to add the FabricPath encapsulation on top of it. Specifically, what we need to know is what is in the outer destination address. This is going to be the switch ID of the exit node out of the fabric. So let's say, for example, we're trying to get from server A to server B. When the frame enters here, the source MAC address is going to be A, and the destination MAC address is going to be B. We then take this entire frame and we're going to put a FabricPath header on it. We're going to say now the outer source address is going to be this switch X, and the destination address is this switch Y. Now when the frames go into the middle of the network, the only thing that these spine nodes need to look at is what is the destination switch ID in order to leave the fabric. So I don't need to learn about A and B. The only thing I need to learn about is X and Y. So when you look at this from a scalability point of view, there's going to be much fewer switches in the network as there are going to be end hosts. Because the point of the switches is to aggregate all the connections for the servers. We might have 100,000 physical servers in the network, but we might only have 1,000 or 2,000 switches in order to do the physical connectivity between them. So instead of switching based on 1,000 MAC addresses, we could do routing based on 1,000 switch IDs, or 100,000 MAC addresses, I should say. Whatever the larger number is, we're doing the routing now based on a much smaller subset of information that we need to advertise between the switches. Now, as someone had asked here, is there a reason to not use, oh, I read that question wrong. I thought the question was, is there a reason to not use spanning tree over FabricPath? The reason why you want to use FabricPath is that if this was spanning tree, only one of these ports would be root and the rest of them would be blocking. So we could forward that way, but we would not be able to forward this way and this way and this way at the same time. This is what FabricPath is allowing us to do. So instead of having just the triangle topology like we have here, we have an arbitrary number of switches in the fabric. Okay, so the question was, is there a reason not to use FabricPath? Yes, there are some reasons. The main reason is not all platforms support it. So the 5K, the 6K, and the 7K run FabricPath. Technically, the 2K does because the 2K is just an extension, a port extension of the upstream switch. But you cannot do interoperability to other platforms that don't run it. So if you have like Catalyst 6800, since it doesn't support the hardware feature, you're not able to put that switch into the fabric. But you don't necessarily have to run it end to end. You could say certain portions of the network are going to run FabricPath in order to get dense layer 2 connectivity, and then other portions are just going to run regular layer 3 IP routing in order to get routing connectivity. Now this does also assume though that in order to route out to the final destinations, we're still going to have some sort of layer 3 edge. So let's say that we have server A is a web server. And then in the IP network, somewhere we have our end host, our client, that's trying to send traffic to the web server. Well, the client and the web server, they're not going to be on the same VLAN. They're not going to be on the same subnet. So we have to do layer 3 routing in order to connect these two together. This means that you would have to have another set of switches, which are sometimes called the, I believe they're called the edge leafs, is the term. Which the edge leaf is running FabricPath on one side and then layer 3 routing on the other side. So FabricPath it's a layer 2 technology only. If you have a server in VLAN 10 trying to reach other servers in VLAN 10, you can use FabricPath for that. But if you need to go between VLANs, to go between subnets, you have to go to a regular layer 3 router, and that's going to be a FabricPath edge device. So the FabricPath spines, they don't do routing. They're doing just regular, well, not regular. They're doing layer 2 FabricPath routing as opposed to regular layer 2 switching. There's a question, VPC can forward over 2 links at a time. What's the advantage to use FabricPath over VPC? Because FabricPath can forward over 3 or more links at a time. Where VPC, we have a very strict set topology, and it becomes difficult to scale that, because if you think of in terms of a virtual port channel, there's only one physical supported topology. It's 2 upstream switches that are connected to the downstream node. So at some point, you're going to run out of ports on whatever these upstream switches are. Even if there are 77 18s, if you say I have 18 slots of 48 ports, it is pretty dense connectivity, so what, 48 times 18, 800 and some ports, but still at some point, you're going to run out of connectivity that goes to the leaf nodes. Then if you want to add additional spines, VPC wouldn't support that, because spanning tree would then go active standby forwarding, where FabricPath allows you to go active, active, active forwarding. So to scale the network, you simply add more switches into the spine in order to add more physical port density. There's another question, is the traffic load balanced? Yes, it is. So instead of doing load balancing at layer 2 like we do with a port channel, we do load balancing with the routing process logic, where we have equal cost routes between the switches. So think of it this way, like a regular, let's say 2 regular IP routers. You have router 1 and you have router 2. We connect them together with a routed link. We'll say that this is the 10.0.0.0 network, let's say /24, and then we connect them with a second link. This is 20.0.0.0/24. Then we have 2 different LAN segments. We have 1.0.0.0 and we have 2.0.0.0. So we have a host A that's trying to reach B. From a layer 3 routing point of view, when the packet goes this direction, router 1 is going to say, I have a route to the 2 network via this interface and via that interface. Assuming that the routing cost is equal, like the OSPF cost is the same, the EHRP composite metric is the same, the ISIS metric is the same, then we should be able to do load balancing between those 2 links. Now, how the load balancing occurs is going to be up to some sort of hashing mechanism. Like in the case of the routers, that's where they use Ceph for load balancing. In our case, FabricPath is going to make the decision based on the upper layer information, like based on the port numbers, it can do hashing to one link over the other. So if this was a FabricPath network, the only difference is that instead of running IP in the middle, we're tunneling this over FabricPath encapsulation. And we would basically be saying that these 2 routers are now switches, where we have multiple equal costs from router 1, or basically switch 1, in order to reach R2 in the fabric. So then if we have A and B here, we would say in order to get from those 2 switches, to get from R1 to R2, we can go this way, or we can go that way. As long as the metric values are the same, then we can do load balancing between them. So if they're both 10 gig ports, or they're both 40 gig ports, or both 100 gig ports, then we should be able to do hashing between both of them at the same time. But the key is that we don't necessarily need to configure any port channeling. We don't need to configure a VPC. Just based on underlying routing logic, we can load balance the traffic between the different interfaces. And there's a question here, is FabricPath Cisco's version of Trill? That's exactly what it is. So Trill, it was meant to be an Ethernet in Ethernet routing protocol, that it's a transparent interconnection of lots of links, TRILL. FabricPath is a pre-standard implementation of that. It's just a proprietary version of Trill, basically. But since it's not Ethernet in Ethernet routing, it's Ethernet in FabricPath routing, it means that you can only do it on the platforms that have the FabricPath ASICs. So where a regular Ethernet switch, like a Catalyst 3750, it has Ethernet ASICs, it doesn't have FabricPath ASICs. That's why in the case of the Nexus 7K, it's not supported on all of the line cards, because not all of the line cards have it hardware accelerated. So if you go to cisco.com/go/nexus and we go back to the specifics of the part numbers, so products, Nexus, 7K models, and we look at the M cards do not have FabricPath support. So it's only on the F cards with this feature beyond. For this reason, in a lot of real designs, you don't use Nexus 7K as the FabricPath spine. You would use something like a Nexus 6K that has lots of bandwidth and lots of port density, and you would use it just for doing FabricPath switching. Then something like the 7K would be your layer 3 edge, where you would connect it into FabricPath, but then you would also put, that's where your default gateways would point to from the servers.